Okay, everybody, this is Advanced Topics 2.5, second of the marking period. Advanced Topics Hybridization of sp and d orbitals. Let's see if I get my little... Oh, it makes me so happy. It turns out that there's more that we can say about bonds individually, and there is another phenomenon called hybridization. Let me mention that right now. It's nothing you'll ever have to define. But when we say an atom is hybridized, it means that we're taking what we call pure orbitals and we're blending them. It's as though that we would take let's say a lion and a tiger and make a liger. It's a rough analogy of this. If you remember, when we first were drawing dot diagrams for atoms, we said the pure way of doing it was this. We put 2 at 12 o'clock, 1 at 3, and 1 at 6 o'clock. And I'm not sure if I said it at that time, but these represent 1, 2, 3, 4 pure orbitals. This is a pure S, this is a pure P, this is a pure P, and this also is a pure, albeit empty, P orbital. Now, the way that we drew it, I think even maybe followed my lead, I preferred to draw it the alternate way, even though I said both are correct. The difference is that these are no longer pure SPP orbitals. These are what we call hybrid orbitals. In this case, what this has become, perhaps, is this has become a hybrid orbital, sp3, 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 and sp3, meaning that I took an S and 3 P's, I put them in a blender, and I, in effect, wound up with a hybrid orbital that was 1/4 S and 3/4 P. Again, it's not important that you know how these came about, but simply that it exists. What you guys are going to have to be able to do is to determine the kind of hybridization that governs that central atom. I'm just explaining in a very, very superficial way how hybrid orbitals come from pure orbitals. Okay, we're going to come back to that in a moment. But first, I want to talk about the bonds themselves. And this is actually kind of interesting. We have what we call sigma bonds, and we signify sigma. Sigma is actually a Greek letter, and that is one way of writing sigma. And the other is pi. You guys know pi from math. Pi here signifies a certain kind of bond overlap. Now, all you guys are going to have to tell me is the following. If you have a single bond, you'll have to be able to tell me, well, Mr. Segelke, that is a sigma bond. Single bonds are always sigmas. A double bond, one of the two bonds is a sigma, but the other bond is what we call a pi bond. And finally, if you were to see a triple bond form, it could be a triple bond between C's or N's, it doesn't matter. All triple bonds are the same in that one of them is a sigma bond, and the other two are what we call pi bonds. Now, even though that's all you have to be able to tell me, I would feel that it would not be satisfying to you not knowing what the fundamental difference is between a sigma and a pi bond. Well, let's look at that sigma bond as an overlap of two orbitals of bonding electrons. Well, it turns out here that a sigma bond just means that two orbitals are overlapping head-to-head. That's all a sigma bond means. Now, if you notice, since I have a pair overlapping geometrically here, this location is no longer available to bonding. So that means I next have to rely, if I want to form another bond between these two atoms, I have to rely on something called a pi bond, in which they overlap these orbitals side to side. So again, I call this overlap head-to-head a sigma bond, but I call this side-to-side one a pi bond. Now, what about a triple bond? I can't overlap side-to-side here and here again. That space has been taken. What's left to me, and this is really tough to see, it's hard to render 3 dimensions on a 2-dimensional surface, But you have to imagine that this one is coming out of the screen at you, and this is going away into the screen, maybe into Mr. D'Angelo's office. This one is also coming out at you, and if you notice, these are also overlapping side to side. So notice I have my sigma bond overlapping head to head here. I have two p orbitals overlapping side to side. That's one of my pi bonds. And the other pi bond is coming out, poking you in the eye right now. So that's how we get. Now, it's a mess, I realize. But at least I wanted to show you approximately the difference between a sigma and a pi bond. Okay. Well, let's move on then to talking about hybridization. Well, what you're going to have to do, let me give you the approach. You will draw on your homework a dot diagram for a molecule. And using that information, you are going to count up the number of effective pairs on the central atom or on the atom that I specified. This is very important. You do not count up all of the effective pairs on all of the atoms, just on one of the atoms, most typically the central atom. But I first have to define, what do I mean by an effective pair? Well, an effective pair is one of two things. Firstly, it could be a single, a double, or a triple bond. We don't care whether it's one pair of shared electrons, two pairs of shared electrons, or three pairs of shared electrons. They both have a similar function. They are both what we call an effective pair. So a single bond is one effective pair, a double bond is one effective pair, and a triple bond is also one effective pair. You also count non-bonding domains as effective pairs. Non-bonding pairs. So let me look at two of them. Let me take our old friend water, since that's really easy. I will ask you right now, how many effective pairs are on the central atom, meaning oxygen? Well, I said a single, double, or triple bond counts as an effective pair. So I have a single bond and another single bond. Those count as effective pairs. And don't forget, these non-bonding pairs also count as effective pairs. 1, 2, 3, 4 effective pairs. Let me give you another one. How about if we had this one for CO2? I'm going to draw the molecule out. But if I'm asking you how many effective pairs there are, it's almost always the central atom, or I could specify on another atom. But let's stick with the central atom. So notice I have a double bond here on the central atom, and I have another double bond also on the central atom. Each of these count as one effective pair. So that carbon has two effective pairs. Now, if by contrast, what if I specified this oxygen there? Well, in that case, I'm only looking at the bonding domains and non-bonding domains around the oxygen. So again, I have one double bond touching this oxygen. I have a non-bonding domain and a non-bonding domain. So I have a total of 3 effective pairs on that particular atom in this particular molecule. Okay? So this is simply a test you have to run as soon as you have a perfectly drawn dot diagram. Let's go to the back sheet. So what you'll see on this sheet, maybe you have the blank sheet in front of you. I can't easily scroll down right now, but what you see is I have 2, 3, 4 effective pairs. Down here, I also have 5 and 6 effective pairs. Now, let me tell you, these are all examples, by the way. This is an example of a molecule, one of whose atoms has 2 effective pairs. Now, when we say that you have 2 effective pairs, again, if I'm looking at this nitrogen, I have a triple bond that's touching it, and a non-bonding pair. That's 1, 2, that's 2 effective pairs. What kind of hybridization is that? Well, it turns out that if I have 2 effective pairs, that means I took 2 orbitals and hybridized them. What did I do? I took an S and I took a P. So I have 2 letters, so that is 2 effective pairs. Another example of two effective pairs would be in this molecule. This carbon atom is touched by a triple bond and a single bond, also two effective pairs. Hi. Oh, sorry, there was a knock at the door. Okay. Next. Oh, let's not forget, let's do a little practice here as well. Let's count up the number of pi bonds and sigma bonds here. Well, notice pi bonds, we'll start with the sigma. Sigma and pi. In a triple bond, remember one of them is always a sigma and the other two are pi. So very simply, I have two pi and one sigma. In this molecule, and I look at the entire molecule, not just on one atom, notice I have single bond, that means sigma, sigma. And again, in the triple bond, one of them is a sigma and the other two are pi. So I have a total of five bonds, right? A total of 3 sigma and 2 pi bonds. Okay. Now, if I have 3 effective pairs, that means I took a total of 3 orbitals. I took an s, a p, and a p, and I hybridized them. That means we call that sp2. Now, how are there 3 effective pairs on this atom right here? Well, I have a double bond that counts as 1, a non-bonder, and another non-bonding domain there. That's for a total of 3. If I look on this molecule, on that carbon, I have a double bond that counts as 1, a single and another single. 1 plus 1 plus 1 is 3. In this molecule, double bond, one of them's a pi, one's a sigma. In this total molecule, I have sigma bond, sigma bond, sigma bond, sigma bond. Then one of these is a sigma bond. That means 5 sigmas and 1 pi. Moving on to 4 effective pairs. If I have 4 effective pairs, that means I took a total of 1, 2, 3, 4 orbitals. I took an s, a p, a p, and a p, and I put them in the hybridizing blender, and I made something called sp3. So that means if I have 4 effective pairs, one of them is this non-bonding domain. Then I have 1, 2, 3, 4. That's the 4. On this molecule, that carbon has a single bond, single bond, single bond, single bond. That's 4 effective pairs. Let me scroll down. Now, these are the interesting molecules from that lesson on DSCPR. They're interesting because the central atoms both have more than 8 valence electrons. How is that possible? Well, if I just had S, P, P, and P, that's 2, 4, 6, 8. 8 is not enough. If we look over here, on the S, I have a non-bonding domain and 1, 2, 3, 4 bonding domains for a total of 5 effective pairs. That means I have to then dig deep down into the atom and pull out a D and throw that into my hybridization as well. Of course, formally I write this as being sp3, and we put the D in front. That's the hybridization. Well, how many pi bonds are there? Well, guys, there are no double bonds, no triple bonds, so there are no pi bonds. I have 1, 2, 3, 4 single bonds, so 4 sigmas. And we have just enough time to talk about 6 effective pairs. For example, in this molecule, you draw this one. Notice I have non-bonding domain, non-bonding domain. And then I have a single bond, single bond, single bond, single bond. That's a total of 6 effective pairs. So that means I have an S, a P, a P, a P, a D, and a D. 6 orbitals. We call it D2 sp3. Final thing, I want to count up the number of sigma and pi bonds. Again, no doubles or triples, so no pi. And I have 1, 2, 3, 4 single bonds, so that's 4 sigmas. All right, my friends, that is a hybridization. So what I would recommend is you commit these SP, SP2, SP3, DSP3, and D2SP3 to memory, although you can easily conjure them from memory by remembering that that's 2 letters, that's a total of 1, 2, 3 letters, 4 letters, 5 letters, 6 letters. Okay, I hope that was helpful. Bye-bye.